Hello everyone, let's get started on the heating curve. So let's review what we've learned about phase changes. First, what is a phase change? A change from one state of matter to another, right? So we have talked about solids, liquids, and gases. What does endothermic and exothermic mean? So endothermic is absorbing heat and exothermic is releasing heat. In addition to just solid liquids and gases, let's talk about the names of the phases so to make sure that everyone knows exactly all the names. So we do know that endothermic means energy is absorbed. So you can go from a solid to a liquid to a gas if energy is put into the system. So one thing that I think we've mentioned, but briefly, is if energy goes in and you go from a solid directly to a gas, we call that sublimation. Shorter steps, when you go from a solid to a liquid, we call that fusion. You know it as melting. And when you go from a liquid to a gas, vaporization, and you probably know it as boiling. In the reverse direction, in an exothermic process, when energy is released out of the system, to go from a gas directly to a solid is called deposition, where to go from the gas to the liquid is condensation, and then to go from the liquid to the solid is solidification. Things to be thinking about and considering are what actually happens to energy as matter moves from a solid to a liquid to a gas. So in the endothermic situation, we know that energy is being absorbed, and we talked about kinetic energy, and that kinetic energy is measured through temperature. And so if the kinetic energy is increasing, the heat is moving into the system and kinetic energy is going up, the temperature is increasing also, and the potential energy is increasing. And we haven't talked about why the potential energy is increasing in much detail. But when you think about potential energy talks about the position of two things in relation to one another. So for our purposes, we're thinking about the molecules and the distance between the molecules and the separation. So potential energy will increase when the molecules' separation increases. In regard to kinetic energy and potential energy, we'll talk about these specific types of energy when we look directly at the heating curve. So knowing that all of you are very curious, you ask yourselves, what happens when we keep adding energy to a solid? Well, I think just based on our conversations in class and your life experiences, you know that the solid ice will become liquid and then the liquid will become a gas. So if you look at this particular graph, it says as the temperature goes up and increases and time occurs, that all of a sudden we have this perfect uniform increase. Well, is that true? As energy is increased and kinetic energy is increased, does the curve look exactly like this? And the answer is going to be no, and we're going to talk about why that answer is no. So what does happen if the temperature doesn't uniformly go up? What happens is described by what we call a heating curve, but I'd also like to show you a time-lapsed demo courtesy of Mr. Grotsky. So here you see the heating curve of water. So you have a beaker with ice in it, and you can't quite see it, but it's on a hot plate, and continuous heat is being added to it. So hold on, let me just increase the size of the screen. So what you're seeing is time-lapse video, so it's going to go quickly, something that actually took 20 minutes to occur. So the temperature is staying the same, predominantly staying the same over time, because if you look in here, there's still ice remaining, and it's turning to water, you can see more and more water and less ice. Once all of the ice disappears, look at what happens to the temperature. Now, all of a sudden, the temperature is very quickly on the rise. Again, remind yourself that heat is continuing to be added to this situation, this system. Now, you can see that the water's starting to boil. So, oh, during boiling, it started to flatten out again, meaning what was happening to that energy? So I know that that video was a little bit hard to describe without us being in person. So I'll show it to you again in class. But all in all, what I need you to understand is if we heat a solid, its temperature increases steadily until we finally reach a temperature at which the solid begins to melt. It begins to go through a phase change. The solid turns to the liquid. And notice, as you can see from this slide, it says, as the solid begins to melt, something unusual happens. So while heat is being added, that ice was on a hot plate. So the ice started at a very cold temperature. And as it sat on the hot plate, the ice got warmer. But all of a sudden, it hit 0 degrees. And that's where we always say, by definition, that we know that things melt or freeze. But look at this. While the ice was changing or transitioning from a solid into a liquid, the temperature did not change. So as we continue to add heat the solid, the temperature stops rising as the solid continues to melt. And you have to ask yourself, but why does this happen? So solids exist in a rigid, closely packed, highly structured pattern. We continue to talk about this structure, this lattice. Liquids, however, don't have the rigid structure. So as the solid is turning into the liquid, it's reached its melting point. There's just enough energy for these intermolecular forces, in other words, those little individual molecules, for them to start to break free from this particular structure and shape. So the molecules begin to separate. So here's another way to visualize it. The energy goes in to take this one little molecule and have it break free. And this way the molecules don't have to be in this particular arrangement, but instead can be in a more loose arrangement, and they have more separation between them. So now that we saw the time-lapsed demonstration, and I just showed you the pictures with the little red and black dots representing the individual water molecules, you can really, I think, put a mental picture to this concept of heat of fusion. The added additional heat energy goes into separating more and more molecules. As these molecules move from the solid to the liquid phase, the potential energy increases, but the temperature doesn't rise. The kinetic energy remains constant. The kinetic energy, remember, we measure that with temperature. So the energy necessary to melt 1 gram of a solid is called heat of fusion. Okay? Fancy term to describe the energy needed to break the molecules, to separate those molecules from the solid to the liquid phase. Okay? This is also going to be unique for every substance. For water, the heat of fusion is 334 joules per gram. So again, the heat of fusion will be changing the arrangement of the molecules from here to more of a situation that looks like this. And when you're looking at the heating curve, you have the solid ice cubes, and it stays solid, solid, solid. And then once you hit this point, the solid ice cube, the molecules start to rearrange themselves, the molecules start to rearrange themselves, and they continue to rearrange themselves until eventually you're no longer in the solid phase and now you're in the liquid phase. So this again is what the video demonstrated. The images here will demonstrate, and now you can see it drawn another way on a heating curve. Notice if I take any point on this flat line and I ask you to read this graph, you go across and the temperature is 0, because during a phase change, the kinetic energy does not change, but rather the potential energy increases. The separation between the molecules increases. And another important thing to point out is remember, heat always flows from hot to cold, from hot to cold. Remember those little E's that we saw moving last week or a couple days ago. Until the last piece of the solid melts, the temperature of the solid liquid mixture will remain constant. That's what we saw on that video, that there was a temperature probe inside of that beaker with the ice cubes, and the temperature really did not change until all of a sudden all of that ice changed into a liquid. And the only reason there was any increase at all, because remember this was an experimental demonstration, is because the ice and the water mixture was not being evenly stirred. If that was the case, you would have gotten a constant temperature. So any excess heat in the liquid immediately flows back into the colder solid. Once there's no solid left, all the additional heat begins to increase the temperature of the liquid. Remember that all of a sudden there was that dramatic rise in the temperature of the ice-water mixture. Once it turned to all liquid, all of a sudden the temperature shot up. So as you start to look at this heating curve, you should be able to read certain information off of it. So when you look at -10 to 0 degrees, that is simply the solid phase of the water. And as you can see, the temperature is increasing. It's going from -10 to 9 to 8 to 7 to 6. It goes all the way up to 0 degrees. So the kinetic energy, the temperature is increasing, but the potential energy is being held constant because remember, all those molecules are right next to one another. Their position has not changed. Now, if we look at the solid turning into a liquid, that melting point, the temperature now stays at 0, but the rearrangement of the molecules begins, so the potential energy is increasing. And then if we take it a step further, we hit the liquid phase. That liquid will, when it all turns to a liquid, be at 0 degrees, but heat is continuing to be added. So all of a sudden the temperature rises within the liquid. So when temperature rises, the kinetic energy increases, and the molecule arrangement stays constant. The potential energy stays constant. So when we now move on to that liquid increasing in temperature, and all of a sudden you get to a point where we know that 100 degrees is when water boils. So what happens at that 100-degree mark? Well, now again, the molecules are going to start rearranging because they're going to go from the liquid phase into the gaseous phase. So this is called the heat of vaporization. Molecules in the liquid phase form a close but loosely organized structure, and then molecules in the gas phase have no structure and are widely spread apart. Let's look at that picture again. Hold on. So this is the model that I want to use for you to get this point. So we had the solid in that perfect pattern, and now we have the liquid where they're not exactly arranged so perfectly, and they're more loosely bound. Then when we move to the gas phase, they are very far spread apart. Now you can see the individual molecules, and they're no longer limited to the container. A liquid is limited to its container. A gas is not limited to its container, so its potential energy continues to increase. So back to this slide, the heat of vaporization, which is what it's called when the molecules go from a liquid to gas, it takes a lot of energy to separate these molecules, and this energy is called the heat of vaporization, and we'll continue to talk about that. And take a moment to look at it from this perspective. We talked about how the solid changes to the liquid at 0 degrees, and now look, the liquid is changing to the gas, and it's 100 degrees. Any point on this line is 100 degrees. You start with your all liquid, and then partial liquid, partial gas, partial liquid, partial gas, partial liquid, partial gas, and then you go, when you're at the end of the phase change, to total gas. And then once you get into the gaseous phase, the temperature can continue to rise. there's no limit here. So as long as the liquid is boiling, the temperature and the kinetic energy will be constant as long as the liquid is at its boiling point. But the potential energy will increase right here. The distance between those molecules will increase. So in summary, during the phase changes, solid to liquid, and then up here, liquid to gas, the temperature is constant, the kinetic energy is constant, the potential energy increases along this line here. We have constant temperature, constant kinetic energy, but the potential energy is increasing along these two phase changes. From solid to a solid that approaches its melting point, temperature is increasing. Kinetic energy is increasing, but potential energy is not increasing. From liquid up to a liquid that begins to boil, something that just turns into a liquid, and then a liquid that's about to boil, the temperature is increasing the entire time. The kinetic energy is increasing the entire time, but the potential energy is kept constant. And then once you have the creation of steam, the temperature is going up, the kinetic energy is going up. That is how you need to look at, evaluate, and understand a heating curve.